Okay, thank you. So, first I convey my thanks and gratitude to Dr. Dawson to give me the opportunity to deliver some of my research findings uh, around in front of this kind of gathering. I would be very happy if we can go and participate in person, but somehow I could not. So, by the beginning of the talk that my lecture, the topic is approaches towards the development of green and sustainable protocols. So, sorry, excuse me. So, we start with the green chemistry principles. So we know that the two are principles of green chemistry. This is well known. All these prevention of pollution, certain economy, less synthesis. But I am very much interested on the catalysis. I am working on the field of catalysis. So mainly I will focus on the synthesis of some biologically active or biologically relevant heterocyclic compounds by the application of these various green catalysts, which may satisfy few of the green chemistry synthesis. Not all the 12 principles. It is very difficult to satisfy all the 12 principles, but I try to minimize the waste production or environmental impact of the protocols. So that's why it is a very basic definition of the catalysis that it reduces the activation energy of the system and reaction go fast. So that is called the positive catalysts, and we use catalyst in many reaction and synthesis of various field. Without catalyst, I think it's very difficult to synthesize many compounds, or maybe the cost of the process will be very high, or some other thing, other disadvantage will be there. So catalyst typically, there are two types of catalyst. One is homogeneous catalyst and another is heterogeneous catalyst. Homogeneous catalyst, we know the reactivity, selectivity, all these are very high, but the problem of the catalyst is separation from the reaction mixture. Separation of these catalysts from the reaction mixture. Next, the heterogeneous catalyst, though its separation is easy, but its selectivity and reactivity is very little less compared to the homogeneous catalyst, because the exposed surface area is less compared to homogeneous catalyst. So to get rid of this problem, what scientists developed, we know that they synthesize they develop nano catalyst. It bridge between the homogeneous and heterogeneous catalyst. So this is the nano catalyst. The nanometer is belong to 1 to 100 nanometer. It has large surface by volume ratio, so that's why its reactivity is very high compared to the homogeneous catalyst. But and it also can be separated by some easy technique like centrifugation filtration. But the disadvantage also associated with this nano catalyst is that lifetime. The catalyst is sometime agglomerated in very less time period. So the stabilization of the catalyst is one of the biggest challenge. So people are using some stabilizer agents like silica, alumina, clay, zeolite, metal organic framework, and also some surfactant, some polymer they used for stability. But among all the stabilizing agent, I find my interest goes to the carbon material because it is green, that graphite or graphene oxides. And also this can be it has a dual role. It can be act as a catalyst support, solid support, or it can act as a catalyst also, because you know that in the graphene there is a carboxylic acid group, hydroxyl group, epoxide group. So this is acidic in nature. So acidity is 4.5 pH. So we can you would exploit this acidity also. So these are the graphite, and this is after oxidation it convert to the graphene, and then after rigorous sonication it convert to the graphene monolayer. Now this graphene, now I try to synthesize that various. In the beginning I told you that I try to synthesize various biological active compound. First, I start with the benzodiazepine. We know that benzodiazepine is very important class of molecule. It shows anti-anxiety, antidepressive, anticonvulsant, anti-inflammatory, and sedative hypnotic activity. It is a very useful drug. So the basic structure, these are the few bioactive compound. So our target is to synthesize this basic moiety of benzodiazepine using green pathway. So then, if we go the previous literature review, people are using amber light 15, silver nitrate, then the surfactant DSA, then APTS, all these things they used. But I used graphene, graphite oxides as a potential catalyst for the synthesis of benzodiazepine. Okay. Now this is a model reaction, diamine and chalcone. It is very easy to prepare in the laboratory, and diamine is readily available, commercially available compound. When we try the model reaction in presence of graphene, we got very good yield of the benzodiazepine. So after getting the good of the yield of the benzodiazepine, we standardize other reaction parameter, and like solvent. If we go the solvent screening, we did the solvent screening, and in the solvent without solvent free reaction condition shows the maximum yield of the reaction. Similarly, that catalyst loading, we did the catalyst loading experiment, and you see 25 mg of catalyst is showing the maximum yield of the reaction. So here, sorry, here the 20 mg of catalyst giving at 80 degree is very good result, 89% yield, and here also in 30 minutes, 20 mg of the catalyst geo at 80 degree in 30 minutes it producing 92%. There may be one question may arise that why that it with 7 hours it gives less yield. Maybe this is due to the degradation of the final product that we got the less yield. So that's why we reduce the time in 30 degree, and we saw that it's best yield we are getting. Then we made a lot of derivatives among with this benzodiazepine. Here we did the various substituted diamines, okay, disubstituted and hetero or diamines, orthopyridine diamines. Then chalcone with various substitution, okay, chalcone with furan and 4-hydroxychalcone. All these things we take, and we got the very good result of the corresponding products. Then we shift our protocol. Then we shifted our protocol for the synthesis of this benzodiazepine with using the ketones instead of chalcone. We use ketones. Here also we get the benzodiazepine with a quaternary carbon center, and here also we made the various derivatives, and we tried with synthesis of from various aromatic ketones. Okay. So these are the quite high yield you get. And after the gram scale reaction, we examine the gram scale reaction, and we get good results also in the gram scale reaction. To make this procedure more industrial viable, so we did the gram scale reaction. So this is the possible mechanism. So here that which acid group on the graphene it first activate the carbonyl carbon, then sheet base is forming and one for addition to give the benzodiazepine product. Or if we get the ketone first is acid group activates the ketocarbonyl, then intermolecular cycle, then attack takes place from imine, then both the imine will form, then intermolecular rearrangement will get the benzodiazepine product. So after the reaction, so as I told you that my focus is to develop some green protocol. So reusability of the catalyst is one of the important protocol in perspective of the green chemistry principle. So we tried, we reused till 9 cycle, and we got the very good yield. There is a very less decrease in the product yield till 9 runs. So we can increase in that the runs, but I stopped it here. It does not mean that after 9 runs the reaction rate falls abruptly, but not like this. So we stop the reaction here till 9 runs. It can be increased to many runs. Then after that, the reaction, after completing the reaction and the usability, we took the reuse catalyst and we check the morphology. And we take the morphology and this one. So we check. Then we took the powder XRD, same team, all the things as in the reuse catalyst, and we saw that very good agreement of the with very good agreement with the freshly prepared catalyst. We took the Raman also, XPS also, everything is fine with matching with the freshly prepared catalyst with the reuse. So that means we can conclude that the morphology and activity remains intact in the reaction. Then we did the same kind of benzodiazepine molecule with the spirobenzodiazepine. Okay, the quaternary center, we were able to develop a quaternary center here. Now the same type of thing we did, we took in case of here we took the E13 as one of the starting material, so and we took the catalyst, we standardize the various parameter. So this is the golden parameter. You can see that 20 mg of catalyst, ethanol water mixture 1:1, 50 degree centigrade, it gives the 87% yield. So actually what we did, actually we tried it that ethanol is giving good result also, but water ethanol mixture is more better than the ethanol. Then we did various, we explore the various derivatives here, and various diamine, various E13 we examine, and various 1,3 diketones, and we made around, I think, more than 30 derivatives here with good yield. Various derivative, I think more than 30 derivative we prepared. So that means this procedure is with the electron donating, with electron withdrawing, halogens, it going fine. So then we did the gram scale reaction, 10 millimole scale, 1 gram scale. So it gives also good results. Structures is more specifically established by the single crystal XRD. Okay. So then this is the probable mechanism. Again the acid functional group of the graphene is activate the carbonyl carbon. Then imine formation. After that intermolecular addition, and tautomerization give the spiro benzodiazepine molecule. Again, we check the reusability till 8 runs. It gives perfect, well good, and we characterize all the parameters to check the stability and morphology of the reused catalyst. Then we use the graphene for the synthesis of pyrimidine derivative here. Pyrimidine is one of the important base, and it many drug molecule contain this pyrimidine moiety. So here, before these are some literature review, they use the corrosive catalyst like acid, paratoluene sulfuric acid, boric acid, silica sulfuric acid, hygroscopic solvent catalyst like AlCl3, FeF3, ionic liquid, nanoparticle they used, but our interest to carbon material, graphene, and graphene gave the very good results here. So here various aldehyde and various aldehyde and 1,3-diketones and diamines, benzothiazoles, benzimidazoles, these are using for the synthesis of this pyrimidine derivative. And we got around here also for generality purpose, we used we prepare around 30 derivatives. Okay, we prepare 30 derivatives, and all are giving very good results. Now, this is the mechanism here that again the acid part of the graphene, it activates the carbonyl carbon, and then intramolecular addition cyclization, it gives the pyrimidine derivative. Again, we did the gram scale synthesis. We did the gram scale synthesis, and it gives also the good results. Then we check the reusability. Same thing in 9 runs. That we check the morphology of the reused catalyst. It remains same. Next, what we did actually, we dope ruthenium ferrite on the surface of graphene for the synthesis of amide bond. So you know that the amide bond is a very important class of functional group, amide, and it is the synthesis of amide is one of the I feel is if we consider top 5 reaction for this one, so amide bond synthesis is one of the important aspect, because many natural products, our DNA and everywhere you'll get the yeah, protein, everywhere you will get the amide derivative. So amide bond formation is very important. So we what we did actually, we take the graphite sheet and then convert to the graphene geo, and then sonicate the ferrite nanoparticle and ruthenium trichloride. Actually, we placed ferrite because to make it separable, magnetically separable. So if we place, we can dope ferrites and no need of sonication or something. So we can separate by the magnetic field. After that, the morphology and everything we check. Due to the time constant, we cannot go in detail. So everything is characterized. Ruthenium is presence of ruthenium is identified. Is oxidation state also identified? Everything we checked. Then we applied. It is in the synthesis of acid to amide, and this is the standard protocol. Ruthenium RGO, ferrite GO at 80 degree, 1.5 hours, it gives 94% yield. We tested the reaction in presence of electron withdrawing, electron donating, halogens, and everything, polyaromatic compounds. Then we convert. We try this reaction in the acetonitrile, cyanide to amide, and we also successful of the preparation cyanide to amide, various amide derivative we synthesized. This is the reaction mechanism. Here without geo, with only geo, the reaction is not moving. So then we use ruthenium. Actually, ruthenium coordinated. This first oxime is forming, then ruthenium coordinated, then and some rearrangement takes place, and we form amide. Here, cyanide it coordinated to the ruthenium, and then oxime, then imine, and after that we'll get the amide. The reusability chart, it we tested till 8 runs. Next, is that palladium geo catalyst for the stereo and reduce selective addition of arenes. Actually, this is one of the name reaction is called CH activation reaction. So here what we did actually, we dope palladium on the geo surface, and then we use alkyne for CH activation reaction. We successfully prepared this alkyne, and the reaction condition is 2.4 mole percent of the catalyst in DCM TFA 1:1 ratio for 3 hours. It gives 81% of yield. Now we tested with various electron donating group, and surprisingly, not surprisingly, this electron withdrawing group does not give any yield of the product. The reaction did not proceed, but only electron donating groups we can utilize for this reaction. And the geometry, surprisingly, the geometry sees all the geometry sees only when we use when you use 1,3,5 trimethoxy benzene, then we'll get the trans geometry. But other case is this due to the C's. Okay. Now we extend the this methodology for the synthesis of coumarin derivative. Here, coumarin, you know, that very important molecule. It is very important in many drug molecule and natural product. You can see we can find the coumarin moiety. So then, what we do it in we take instead of benzene, if we alkylated benzene, if we take the phenol, then we'll get the coumarin. Intramolecular cyclization after CH activation, then intramolecular cyclization, it gives the coumarin derivatives. This is the mechanism. This is not very hard mechanism. Just insertion takes place, then addition, and then reductive elimination gives the product. Everything we did, reusability we did, then reusability, then uh, leaching we did. Actually, leaching test how much catalyst leached out during the reaction. This is very important because the drug development, metal contamination, the product is one of the disadvantage we can say. So if the catalyst is leached low, so that catalyst is good actually. And then we identify the morphology of the reused catalyst by various techniques. Then same type of benzodiazepine we synthesis by copper oxide nanomaterials. Here the starting material is different. It is acyl chloride and alkyne. Then diamine. It gives benzodiazepine moiety. Now what happened? Here this we use ethanol and 60-degree temperature. We get the benzodiazepine molecules. Many in this reaction actually is through a coupling type of reaction. So here not only that graphene will not give the product, but in the copper, first activation through the copper center takes place, then intramolecular addition and intermolecular addition, and it is Michael type of addition, and then intramolecular cyclization give the diazepine molecule. Next, this copper oxide reduced graphene oxide will be utilized for the synthesis of flavone moiety. Flavone is very important class of drug molecules. It shows ACH inhibitor activity, anti-inflammatory, anti-tumor, aromatics. These are this activities it shows. So very good target molecule. Then we synthesized graphite powder to graphite oxide. Then we doped copper oxide. There, all the characterization, I will not go in the details. Then we utilize this chalcone for intermolecular cyclization. It gives flavon. So this is the model. This is the standard protocol. Refluxing in water, copper RGO 10 mg, 30 minutes and 90% yield. Many derivative we prepared. Then what we did actually, this is the general mechanism. Copper first activate this carbonyl carbon. This intramolecular Michael addition reaction takes place, then tautomerization. Now, what we did, our plan is to attach triazole moiety. Our plan is to attach triazole moiety with the flavon. So then, what we did actually, we prepared that alkylated chalcone, and then first we did the flavon derivative, and then the triazole. Okay, the same catalyst. That is one beauty of the reaction. With the same catalyst we can use. These are the things. So we know that this is very well-known figure in our synthetic organic chemistry. We are using every time that Heck reaction, Suzuki coupling, and Hussiten 1,3 plus cycloaddition reaction. We know that this is palladium and copper catalyst. So what we did actually, we tried to develop a catalyst which responsible, which can catalyze palladium catalyzed Heck reaction, copper catalyzed uh, copper catalyzed 1,3 dipolar cycloaddition reaction, everything. So what we did actually, we doped first copper on the surface of GO and then palladium on the surface of the GO. This is elemental analysis. This yellow color is for copper and palladium is green color. So this confirm that both the element dope on the GO surface. Then we applied this palladium copper GO at the Heck reaction, then Suzuki reaction, then also triazole synthesis, 1,3 dipolar cycloaddition reaction, then tetrazole synthesis. Every reaction it went successfully. Then we did first Heck reaction, and then first Heck reaction, then tetrazole synthesis, first Heck reaction, then triazole synthesis. All the synthesis this catalyst does well. Okay, so one single catalyst we can use in many reactions. Now this is the last item that I use now, metal organic framework as the catalyst for propargyl and benzofuran synthesis. We know that metal organic framework is a polymeric compound. Metal polymer, where is a metal node is there, organic linker, generally benzene or aryl groups are there. Then what we did actually, this is the various propargylic compound present in the medicine. So post synthetic modification we did, we took 2-amino terephthalic acid, then chromium MIL, and then with pyridinaldehyde make seed base for the chelation of the copper, and this copper containing metal organic framework was characterized thoroughly, then utilized for the propargyl amine synthesis. This and 15 mg 100-degree in reflux 86% give the best result. We prepare 13 derivative here, and then if we take Salicylaldehyde instead of benzaldehyde. If we take the salicylaldehyde, then benzodiazepine, then benzofuran was forming. So benzofuran is formed. Here 11 derivatives, we prepared benzofuran derivatives. Now the mechanistic study, we propose that first copper activate, copper insertion, then addition CYP base, then addition here in the imine bond, and if there is a wedge, then intramolecular cyclization give the propyl or benzodiazepine. Reusability with that, and reusable, we examine the morphology of the reuse catalyst. So this is my end of the talk. So I am from, this is just 1 minute. I am from Northeastern University in Meghalaya, India. Generally, we tell that this is the Scotland of East. Actually, here the natural beauty is so nice. If I invite all of you to visit our university and our Meghalaya, uh, here some beautiful falls. Then root bridge. This is naturally made root bridge. This is the rubber tree, and this is the roots people are using as a bridge. And this is the river. So clean water, in mainly in winter. So you can see that the river bed also. So thank you for your patience.